Hello, this is Math with Beth, and we are going to do higher order derivatives. And we are also going to take a look at how derivatives are used with distance, velocity, and acceleration problems. So first, higher order derivatives just means instead of just doing the derivative, you're maybe doing the second derivative or the third derivative. So all you do to find a second derivative is start at the beginning, find your first derivative. So hopefully you already know how to do basic derivatives. Right now, I'm just using the chain rule to do that. And now if I want the second derivative, I just do the derivative again. So again, I'm just doing the power rule. The derivative of 1 is 0. So it was just the power rule that needed to be used for these, nothing fancier. But you can still do the same thing even if they are fancier ones that involve chain rules, product rules, whatever. So that's the basic idea. Here is a reminder of all the different ways that first derivatives can be written. So now here's a bunch of different ways second derivative can be written. So this one ends up confusing people a lot because of the squares. They think that there's something that needs to be squared, but this is just another way to write the second derivative. So keep that in mind. I typically just use y prime, y double prime, y triple prime, but you could see these in your books, so don't get confused by those. So the directions for this want me to find the first derivative and the second derivative. So first derivative, I first need to decide, is this a simple problem where I'm just going to use power rules, or is there something more going on here? This is a function inside another function. So I'm going to need the chain rule. So if you do not know how to do the chain rule, I would stop here and go watch a video on chain rule before you keep going. So if you do know, you're going to deal with the outside function first, which is the fact that something's being raised to the 6. So that 6 needs to come in the front. And then you do 6 minus 1 for the power. So that's the first step of the chain rule, dealing with the outside function. Now I need to multiply by the derivative of the inside function, which in this case would just be 2x. That's it. If I can make that a little nicer, like I can go ahead and multiply the 6 and the 2x, I'll go ahead and do that. But I'm definitely not going to do all of this to the 5th power. So that's as far as I'm going. So if I now want to do the second derivative, I need to look at what I have here and realize that in order to do the derivative again, I am definitely going to need the product rule. So hopefully you already know how to do that. And in the middle of the product rule, when it comes time to find the derivative of this, I'm going to need the chain rule again. So for the product rule, I'm going to do the first function as it is times the derivative of the second function. This is where I'm going to need the chain rule to do the derivative of this, since it is a function raised to the 5th power. So the 5 comes out front, and then I subtract 1, but then I have to multiply by the derivative of the inside. So this is just me doing my first function as is. All of this is the derivative of the second function. So for the product rule, we still have to add the second function as it is times the derivative of the first. So once again, it depends on your instructor how nice they want you to make this, but I'm going to at least show you one thing that can be done so you're not confused if you see it done. Now that we have all of this being multiplied plus all of this being multiplied, I can look at these two things and notice they both have a 12 and they both have an x squared plus 2. In fact, they both have 4 of them, since this one has 4 and this one has 5. So I can factor out the 12 that they both have and the x squared plus 2 to the 4th that they both have and see what that's going to leave me with. Over here, if I take out the 12 and this to the 4th, I would still have a 5, an x, a 2, and an x. So I'm just going to go ahead and put all that together, because 5x times 2x would be 10x squared, plus over here, if I take out the 12 and 4 of these, all I'll have left is 1 of those left. So one more thing we could easily do to make this a little nicer is at least combine what we can in here to get 11x squared plus 2. So that's just one example of what kind of reducing you could do at the end when you have these really long derivatives. But that's the idea. Now, for distance, velocity, and acceleration, you are typically going to see problems like this when you're dealing with first and second derivatives, because if you have an equation that represents the distance of something, taking the derivative of that gives you the velocity, because the derivative is always the rate that you're going at, which is velocity. If you do the derivative again, it is actually going to end up being the acceleration. So that's something important to keep in mind. So let's do an example that will use that. From the point in which an object is dropped, the distance it falls in seconds, assuming negligible air resistance, is approximately this. Okay, that's a lot of fancy words, but basically they just gave me an equation that means distance. So where S of t is in meters. If a stone is dropped from the cliff, A, how far will the stone travel? So it's asking me about distance 5 seconds after it is dropped. So it's giving me the t. So if they just want to know how far we've gone, I'm just going to use this original equation and plug in what t is, which apparently in this problem is 5. So multiply all that and you get 122.5. Since we're talking about meters, that's my answer. After 5 seconds, it will have traveled 122.5 meters. How fast is the stone traveling? That's referring to velocity. So I need the derivative. So step 1 is to find the derivative of my original equation. So I need to multiply the 2 out front and then do 2 minus 1, which gives me 1. So I don't need to write it. And now again, they gave me a t, so I can plug that in to get my answer. Since we're talking about how fast it's going, this is 49 meters per second. And then finally, what is the stone's acceleration? So acceleration is the second derivative. So here was my original. Here was my first derivative. So I now need to take the derivative again to get the second derivative. So the derivative of 9.8t would just be 9.8. So that means it doesn't matter what my t is. No matter what t is, it's going to be 9.8. So for acceleration, the type of units would be meters per seconds squared. So apparently the acceleration is constant. So it wouldn't have mattered if they asked me for 8 seconds, 12 seconds, whatever. It would still be 9.8 meters per second squared. So there's just an example of how to use derivatives to find distance, velocity, and acceleration. I hope that helps. Let me know if you need more help than that, or if you need more examples, let me know.